Welcome to section 15.6. In this section, we are going to be looking at the concept of triple integrals. So it was so nice to add an integral to give us double integrals. We figured we would add another one to give us triples. Triple integrals are going to be used for functions of three variables, x, y, and z. We're going to look here at some of the similarities and some of the differences between them and double integrals, but calculation-wise, we're really not doing anything different. We're just adding an extra integral into the mix. So that's nice. It's not like we're learning a totally new concept here. But in terms of the derivation, the setup, that sort of thing, if we look at the simplest case of a triple integral, we define a function on a rectangular box. So B is our box with x going from A to B, y going from C to D, and z going from R to S. So that's this box over here. So you can see x is going from A to B, y going from C to D, z going from R to S, like that. So all of these values are functioning as inputs. Now, if we want to work with this, back in Calc 1, we had, an interval from A to B, and we broke it into smaller subintervals like that. In double integrals, we took a region, a 2D region, and broke it into rectangles and found volume over each of those. In triple integrals, we take rectangular boxes out of this entire solid here. So you can see there's a box right here. Okay, and it kind of goes back in there as well. And we can take the values from that box and then evaluate over that piece, and then the next piece, and then the next piece, and the next piece, et cetera, over the entire solid. If we kind of focus in, so you can see there's one right here that I've kind of singled out. If we zoom in, so to speak, if we look at what's going on in here. So we have a rectangular box, and x is changing as we move from this side to this side. So this length here is going to be delta x sub I. Y is changing from here to here, so that side will be delta y sub j. And then z is changing between these two heights for this box, so that's delta z sub k. And this box in particular would be b ijk. So when we find delta x sub I, delta y sub j, delta z sub k, all of those get put together to create delta v, represents the change in volume. Okay, the volume for one of these small pieces, one of these little boxes. Now, what we will then do is we will add up all the values we get for every single box. Oops, so let me just shrink this down here. So we have here a triple Riemann sum. Okay, one of them for x, one of them for y, one of them for z, and we're going to add up across every box in the x direction, the y direction, the z direction, all of them. We add up all of those values, and then if we want to get the exact value of the triple integral, we need to take the limit. So we take the limit as the number of boxes in the direction of x, y, and z, so that's L, M, and N. As the number of rectangles goes to infinity, the number of boxes, I should say, they all shrink smaller and smaller and smaller and give us better and better approximations to the actual value. So when we get to that point, We let the limit go to infinity. That gives us the exact value of the triple integral. So the nice thing, like I was mentioning earlier, is the derivation is basically the same as double integrals, just brought up one dimension. So we work with them very much the same way. So if we're working with a rectangular solid, we can apply Fubini's theorem again. Fubini's theorem will also work for triple integrals as long as we're working over a rectangular box, so all of the bounds are constants. So if that's the case, we get the triple integral of f of x, y, z. We can have it dx, dy, dz, with x going from a to b, y going from c to d, and z going from r to s. Okay. And then, of course, with any order of integration. Since they're all constant bounds in this case. So let's try out an example. So evaluate this triple integral of xyz squared dv, where b that we're integrating over is the rectangular box given with these dimensions. So we're going to get triple integral of xyz squared. Order of integration doesn't really matter here because, again, all constant bounds, but I'll just stick with dx, dy, dz. So x goes 0 to 1, y goes -1 to 2, z goes from 0 to 3. And in terms of the evaluation, we just go one integral at a time. So we evaluate the innermost integral with respect to x. So that's 1/2 x squared yz squared. Evaluated from 0 to 1. And dy dz is still out there. So we get just 1/2 yz squared. Dy dz. Evaluate with respect to y this time, so that's 1/4 y squared z squared from -1 to 2 dz. The 2 gives us a 4/4, so that's just z squared minus 1/4 z squared. So that's going to be 3/4 z squared dz from 0 to 3. So we get 1/4 z cubed from 0 to 3. So we get 27/4. Okay, so the process of actually integrating does not change. We still use that partial integration where we treat the other variables as constants while we work with our current variable, and we just have to do it one extra time. In this case, because the bounds are constant, one of the results of Fubini's theorem was that you could split up constant bound integrals into separate single integrals as a product if you could split the functions up, which we absolutely could have done here. So you could have set up the dx integral, the dy integral, and the dz integral separately as a product of each other because of the way that this function is. That's not necessarily something you have to do, but it can simplify the work a little bit if you notice that, if you recognize that relationship. Now, just like how double integrals are not all performed over rectangles, triple integrals are not all performed over rectangular boxes. So we need to look at the types of regions that we can work with, or I should say the types of solids that we're going to be working with. And because we're in 3D, in 2D, when we were doing the double integral, the region D was either integrated vertically or horizontally. That was really the only two choices we had, unless you convert to polar, but that's a whole different story. In 3D, there will be 3 different directions that we could set up our integration, okay, in terms of bounding the 3D portion of the function. So this is what we call type 1. And this is why when we do double integrals, I don't like to harp on the concept of type 1 versus type 2, because now with triple integrals, we're going to get types 1, 2, and 3. So having to keep straight the terminology of type 1 double and type 2 triple can get confusing. So we'll see kind of how this works in practice. So we're going to define a triple integral over a general bounded region E in R3. So for type 1, we've got z going between 2 functions of x and y, and then x and y are in the domain D. Okay, so if we look over here, we have our solid E here, and we have the bottom function in terms of x and y. We have the top function in terms of x and y. Z is going between the two of them, and it projects down onto the xy plane. So for our triple integral, we can set up the double integral will be over D on the outside. Inside of that, we'll have an integral of f of xyz dz, with z going from u1 of xy to u2 of xy, and then dA for the double integral out here. So when it comes to evaluating a triple integral, the first step is always going to be setting up the 3D integral, the 3D portion of the integration. That's the innermost one. So in this case, because of the way these functions are set up, we have z as a function of x and y in both cases. Z is going to be the inner integral. Once this is done, all you'll have left is a double integral in terms of x and y, and those we can solve using the methods we've seen the last several sections. Now, I want to try to emphasize that because in this next little section down here, it starts to look a little more confusing. So basically, when we have a double integral, it could be type 1 or type 2. So if we tried to set it up as type 1, so notice, just like back up here, z is between 2 functions of x and y. That's this innermost integral here. But then we get y is between 2 functions of x, and x is between 2 constants. So this portion is the 3D part. This is the double integral. Okay, and this is basically telling us that we're integrating vertically because y, right, goes up and down between 2 functions of x, and then x sets the edges as the constants. So as the triple integral, this would look like this. dz, dy, dx, with z from u1 to u2 of x and y. And y is going from g1 of x to g2 of x, and x is going from a to b. Just like in double integrals, we should always have constants on the outermost integral so that when we're done, we should have a numerical value as a final answer. So notice this one is in terms of x and y are still outside of it. This one is in terms of x only, and x is still outside of it. And then once we get to x out here, it's all constants. Now that would be if it was done vertically, but we can still evaluate the double integral portion horizontally, where x is going between 2 functions of y, and y is going between the constants c and d. So that would give us dz, dx dy. Z is still going from u1 to u2. Dx is going from h1 of y to h2 of y, and y is going from c to d. Okay, so again, the 3D component is the same, and then the 2D component, this is being done horizontally. So this one is a vertical double, and this one is a horizontal double. And each of the cases is going to have these pairs where you evaluate the triple integral for the innermost one first, and then you evaluate the doubles either vertically or horizontally. The way that I like to set these up is more in line with the top formula up here, where we set up the 3D portion first, evaluate this innermost integral, and then once that part is done, then we can focus on the double after that. I think that makes it a little bit easier to visualize and a little bit less pressure to try to set up the whole thing all at once at the beginning. You can set them up all at once, but I think it's a little bit simpler, more straightforward to just do the first integral first, get the 3D part out of the way, and then go back to just a regular double integral problem after that. So let's try an example. So as you can see here, I've got some diagrams for us. Evaluate the triple integral over E of z dv, where E is the solid tetrahedron bounded by the four planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. So this is our solid E. And I know it's a little faint, but you can kind of see I've got different colored kind of planes back there hiding behind the top plane. So this green one over here, that's going to be x equals 0. This orange one is y equals 0. This purple one down here is z equals 0. And this top one, this gray one, kind of hovering over everything, that is this plane, which I can go ahead and solve. That's z equals 1 minus x minus y. Like that. So if we focus on solving the innermost integral first, so we're going to have triple integral over E of z dv. So we're going to take the double over d and just ignore it for now. We're not going to worry about the double integral yet. So this one, we can go from the bottom function down here up to this top function up here. So from bottom plane to top plane with respect to z. So we have z dz with z going from 0 up to this plane. So 1 minus x minus y. And then dA. So this is the 3D portion. This is filling in the solid from the xy plane down here up to this plane. Now we can evaluate that. So the double integral doesn't go anywhere, but we can evaluate this. So we get 1/2 z squared from 0 to 1 minus x minus y dA. So we're going to get double integral over d of 1/2 times 1 minus x minus y squared dA. Now we can focus on the double integral, because now that we've done the 3D portion, now this problem is just a double integral problem. And so we can look at the 2D region, in this case in the xy plane down here, that is formed by this solid. Okay, so that's going to be this triangular region D, where this is going to be y equals 0, this is going to be x equals 0, and this line here, that's this line, is formed by this plane. So if z equals 0 for this plane right here, so that's where it intersects along that line, we can get the equation as y equals negative x plus 1 for that line. And we can go ahead and integrate this vertically. So we have this line, this point up here, that's going to be 0, 1. This point, that's going to be 1, 0. And of course, 0, 0 at the origin. So if we set up the double, I'll pull the 1/2 out. We'll just pull it out to the front here. We have 1 minus x minus y squared dy dx, because we're going vertical. Y is going from 0 to negative x plus 1. X is going from 0 to 1. If we integrate with respect to y, you can apply some version of the chain rule when you're anti-differentiating this. Basically, you end up getting negative 1/3 1 minus x minus y cubed from 0 to negative x plus 1 dx. Okay, so basically undo the power rule, but then because this is a negative y here, you have to balance that out with a negative when you take its antiderivative. Okay. Or you could set up something like a u sub and get the same result. But at that point, we could go ahead and substitute in negative x plus 1. If we do that, sub it in for y, we get negative x minus negative x. So that ends up being plus, right? 1 minus x minus negative x, so plus x. So that ends up getting rid of all of our x terms in that one, and then minus 1. So we end up with 1 minus 1, which is 0. So the whole first term turns into nothing. And the 0 term actually does turn into something. We get 1 minus x cubed, right, over the negative 3. So we end up with 1/2 integral 0 to 1. It was minus a negative, so that becomes a positive 1/3. 1 minus x cubed dx. We can pull the 1/3 out, so that's going to be 1/6. Apply the same principle, so we get negative 1/4, 1 minus x to the 4th from 0 to 1. Simplify all that down, we end up getting 1/24 is the value of that triple integral. So we handled the 3D portion first, and then turned it into a double integral problem, and then we solved that using the techniques of the previous sections. Next up, we have here a type 2 triple integral. So when we say type 2, the previous case, the quote-unquote type 1, just projected down onto the xy plane, so it was between two functions of x and y. This one, we have x going between two functions of y and z, so it's projecting back onto the yz plane. Okay, so that's yz. So it projects back onto the yz plane. So again, we have x between two functions of y and z, and y and z are elements of the domain. So for our triple integral, so we get the double on the outside, And then inside of that, we get the integral from u1 of y and z to u2 of y and z of f of xyz dx and then dA. So when we set up the 3D integral first, we have dx going between two functions of y and z right here. And then once we're done with that one, we'll have just a bunch of y's and z's, and we evaluate either dy dz or dz dy, depending on how this 2D region D looks. So we would evaluate that one the same way. So the process of solution is the same. It's just a matter of what direction it's projecting onto, okay, and what order these variables go in. So similarly, we have the type 3, which this, we have now y going between a function of x and z. So that's our solid E between u1 and u2, projecting back onto the region D, which in this case is in the xz plane, okay, because everything is in terms of x and z. And the evaluation for this one, double integral over D, single integral from u1 of xz to u2 of xz of f of xyz dy and then dA for the outer double. So again, same idea, just different order of integration. So again, I'll make the same recommendation that I did with the double integrals over general regions, memorizing them as type 1, type 2, type 3. It's all well and good, but it's not the most effective way to remember them, in my opinion. I find that focusing on the direction of the projection is the most helpful. So you just look at the functions, you see what variables they are in terms of. That can indicate which variable comes first. So like if you see two functions where y is a function of x and z, that's a good indicator that y should come first. And then the double will be in terms of x and z over there in the xz plane. So let's take a look at an example. So we can see here, evaluate the triple integral over e of square root of x squared plus z squared dv, where e is the region bounded by this paraboloid, y equals x squared plus z squared, and the plane y equals 4. So I actually have a little more of an interactive component for this. So there's the plane y equals 4. So notice it cuts off the top part, right? Or I should say the outermost part, the furthest part of that plane. Now, the first inclination, typically, just like in double integrals, we like to integrate vertically. With triple integrals, people like to integrate, again, what we think of as vertically, which would be having z go between two functions of x and y, and doing it on the xy plane. If we do it that way, you can see in here, so it cuts it off here, there is a flat region there that's going to be the 2D region, right? That's D. If we were to set it up this way as a type 1. Now, if we look at what that entails, so we'll do this just at the top here. So if type 1, our region looks something like this. Okay, so this is our region here. That would be D. this parabolic curve. Because we're in the xy plane, z is 0, so this would be y equals x squared. This one up here would be y equals 4. But then when we're setting up the triple integral of the square root of x squared plus z squared, we would have dz would have to come first. And when we're setting this up with respect to z, like here's the xy plane right here, the bottom function is down here. It's the bottom half of this paraboloid, and the top function is the top half of the paraboloid. So you would be going from the bottom half to the top half of the same function. So we would get z equals plus or minus the square root of y minus x squared. That would be, again, the top half and the bottom half if it got split like this. So the z integral would go from negative square root of y minus x squared to positive square root of y minus x squared. And then the 2D region down here would best be done vertically, right? Not horizontally. So we would go dy dx with y going from x squared to 4 and x going from that value to this value. So that would be, right, negative 2 and 2. So negative 2 to 2, like that. And that would be the setup in this case. And this, having a triple integral with a square root of multivariables and evaluating that between two square roots of multivariables is certainly not ideal. So this is not the best way to approach. So we don't want to go into this thinking automatically that doing it vertically with respect to z first is always the best way, because it's not necessarily. So if we go back and look, oops, wrong tab. So if we go back and look, instead of doing that, so here's our surface. Instead of projecting down onto the xy plane like we did, if we project this straight back towards the xz plane back there, we're going to get that projection, right? Going back onto the xz plane, which then forms this outer boundary right there, which is that circle. And then if we take the region within it, that's going to be a circular disk of outermost radius 2, right? Because it corresponds to y equals 4. So we can certainly work with circles. So let's take a look at what this does. So we can say instead, consider projecting onto the xz plane. And again, if we're sticking with their labels, this would be type 3. So we would get the circle, the circular disk within it, and we have a radius out here of 2. So for our triple integral, we're going to set up the double over d, and then the innermost integral, we're going to have y going between two functions of x and z, right? So we have the lower function is the paraboloid, the upper function is the plane up here. So it's going from x squared plus z squared up to 4. So double integral is intact. We take the antiderivative with respect to y. We don't have to worry about the fact that there are x squareds and z squareds in here because they're all constants. We just pick up a y. And then x squared plus z squared in there. From x squared plus z squared to 4 dA. Oh, I forgot to add my dA out there. Be sure to add that in. Actually, I'll just move all of this. All right. Do the evaluation here. We get double integral over d of 4 minus x squared plus z squared times the square root of x squared plus z squared dA. Now this is a double integral problem over the region D, the circular region right here. And if we're working with a circular region, we want to go ahead and convert into polar. The only difference here is that these axes are not x and y in this case. They're actually x and z. So z is going to act like y here. It's going to take the place of y. It's going to be the vertical variable. But we can still convert to polar as we normally would. So convert to polar, and z replaces y because we are in, again, the xz plane instead of the yz plane. So instead of having x squared plus y squared equal r squared, x squared plus z squared is r squared. And then square root of r squared, r dr d theta, with r going from 0 to 2, theta going 0 to 2 pi. We can go ahead and apply the theta trick here. So we're going to get a 2 pi out in front, integral 0 to 2. This is just an r, and this is an r, so that's an r squared. Distribute here, 4r squared minus r to the 4th dr. And now that's looking like something we can absolutely evaluate. So 4/3 r cubed minus 1/5 r to the 5th from 0 to 2. We end up getting 128 pi over 15. So that would be the value of the triple integral of the square root of x squared plus z squared evaluated over this paraboloid solid, okay, bounded between the paraboloid and y equals 4. Now, we've been talking a lot up until this point about calculating triple integrals. We haven't really talked about what the triple integral gives us and what these numbers actually tell us. Triple integrals get a little more theoretical, at least at this point, at this level, than a double integral, because we start working with conceptually things that maybe we don't have as easy a time of visualizing. So when we take the triple integral of f dv, where f of xyz is greater than or equal to 0, when we did a single integral, it gave us area. When we did a double integral, it gave us volume, right? So we went from single integral gave us a 2D area, double integral gave us a 3D volume, triple integral gives us a 4D concept, and it's the same idea as volume, but because it's in 4D, we don't call it volume, we call it hypervolume. So this is called the hypervolume of an object in R4. Because E, that solid that we're working with, E is just the domain of the function. Just like for a double integral, the domain is the region D, the 2D region D, like that. And in a single integral, the domain is just all the numbers from A to B on that interval. But for a triple integral, the domain is actually the 3D object. So one use that we have for triple integrals, beyond just looking at 4D concept, we can look at a special case when the function is equal to 1. And we saw back in a couple sections ago that if you take the double integral of the function 1, it actually just gives you the area of the region, right? The region D. So we said we can use double integrals to actually answer single integral style questions. It's the same concept here. The triple integral over E of 1 dV is just V of E. So this is the volume of E. So not only can we use double integrals to find volume, we can also use triple integrals to find volume as well, if we just take the triple integral of 1. How does this exactly work? Well, if, for example, we take a type 1 region like this, we evaluate with respect to z, the function 1, this ends up becoming the double integral over d of u2 of xy minus u1 of xy dA. And if you recall, this formula here where you take the top function minus the bottom function, this is a concept of integration where you can find like area between two curves, or in this case, volume between two surfaces. So this would give you the volume between u1 and u2. Which, again, is what the double integral would give us. So we know this represents the volume between two surfaces, u1 and u2. And I want us to just notice if u1, if that bottom function was 0, so if the bottom function was 0, then this part would disappear. We would just be left with u2 right there. This gives us just the volume under the surface u2. So if the second function, or I should say if the first function, if u1 is just 0, that's just the xy plane, right, or z equals 0, that type of calculation is what we've been doing all chapter. The idea of taking the double integral of some function, you're finding the volume under that surface. Okay, so there is a direct tie-in between double and triple integrals with this regard. Just to kind of show the relationship in an example, here's an example that we did in a previous section where we found the volume of a tetrahedron bounded by a bunch of planes. So this is all kind of the same diagrams, same kind of setup that we had in that past section. So notice the lower boundary of T. So this is T over here, is this tetrahedron, this whole thing. The lower boundary of it is down here in the xy plane, so that's z equals 0. The upper boundary is this red plane right here. That's z equals 2 minus x minus 2y. So, to find the volume of T, we would set up the triple integral over T of 1 dV. So we could set up the 3D integral first. So this one, we're going to go from 0 up to that plane. So 0 to 2 minus x minus 2y of 1 dz. And then dA. When we take the antiderivative, we get antiderivative of 1 is just z from 0 to 2 minus x minus 2y dA. So we just get the double integral over d of 2 minus x minus 2y dA. And this is where the problem started back in section 2 or section 3, whatever section we did this in. But this is where the problem had started before, getting the volume using the double integral of this function. Okay, that's the surface we're integrating under. Okay, and then I won't go through all the steps of this process again because we have already done this exact problem. But we set up this region. We did it vertically between these two lines that we found their equations. So we got dy dx from 1/2 x to negative 1/2 x plus 1, and then x going from 0 to 1. And we ended up getting 1/3. So we completed this calculation previously. All right, so we can use triple integrals to find volume of a solid simply by setting up the bounds on the 3D portion between the top and bottom function, right? Or the inner and outer, depending on what direction you're projecting it. But now we have made it to the end of this section. I know this one is a long one, and it's kind of the start of the new second half of this chapter, where we're going to start looking at different coordinate systems and properties for triple integrals. So we still got a lot of good stuff coming up in this chapter, but that brings us to the end of this section, and that is our introduction to triple integrals.